Let me start off by explaining what I'd like to do here in the next hour and a half or so. And I want to talk, and to be frank, it's really not so much this program is not so much directed as at an entry level technician as somebody considering actually doing some analysis of shellfish remains. And what I want to do here is first uh, provide some introductory remarks about shell middens and the analysis of shell middens by archaeologists historically, and offer some context to that. And then the bulk of what I want to do is actually use a walk you through a PowerPoint presentation that I developed a number of years ago that actually is a summary of my doctoral dissertation on the marine shellfish from Ozette. And when I go through it, I'm going to kind of treat lightly on the Ozette stuff because it's not primarily tonight a talk about Ozette, as a talk about the range of analyses that one can do with shellfish remains. And it's my hope to encourage people to do more of this type of analysis. And so a lot of what I want to do is to really highlight potentials of what can be done with these types of materials. And let me say, for starters, um, there's no correct single way to study shellfish in a shell midden. There's not one size all approach that fits everything. It depends a lot on what you're interested in and what you want to study. And I will tell you by way of generalization, if you look at the history of shell midden analysis, particularly during the 20th and early 21st century, there's a real dichotomy between analysts working with shell midden deposits and shellfish in shell midden deposits who treat the shell in them as a sediment, and as opposed to treating the shell material in the deposit as representing animals. And I'm not telling you that one of those is right and one of those is wrong. I am telling you, in my opinion, treating the shellfish materials to understand them as animals is going to open up far more opportunities to understand cultural behavior, which I would submit is what anthropologists are primarily interested in. Some of you listening here tonight may be familiar with work that Julie Stein out of the University of Washington did at English Camp in the 90s and early 2000s. And I'm not saying that what Julie did was wrong or anything like that, but I would tell you that Julie's analysis focused on treating the shell material as a sediment, and she was predominantly interested in post-depositional effects in shell middens. And that's a perfectly legitimate thing for a geoarchaeologist to be interested in. Personally, I'm not a geoarchaeologist. I'm interested in understanding behavior. And my point is that we need to go from the shells in the deposit to some standard of talking about animals, and then we can talk about human behavior relative to those animals. And that's a lot of what I want to show you this evening. And let me say something here now also, and I'll talk about it at the end as well. The stuff that I'm going to show you that I was able to do at Ozette was extremely labor intensive. There's no denying that. And even to do these things on a smaller scale than what was done at Ozette, this is a relatively labor intensive kind of analysis. But I'm going to tell you and argue that many types of archaeological analyses are labor intensive. And the philosophy that I'm putting out here, underlying what I'm going to show you, is making investments in your data description so that you have a really powerful database is labor intensive, but worth the effort. And that's what I hope to show. Okay, I'm going to turn the PowerPoint presentation on and then kind of work my way through some background stuff, and we'll wander through this exercise. Okay, so again, I'm talking about OZ, and this PowerPoint was produced for OZ, but I want to talk about a broader range of things. And by the way, just as a small detail, a full disclosure, I like this cover picture. I use it. This is not OZ. This is actually La Push, but it's a shell midden. Okay, so I've given you the introduction and background already. Let's talk a little bit just about some background issues. And archaeologists have been interested, and anthropologists have been interested in shell midden sites and shellfish as a resource for the better part of 200 years in a modern sense. And there are a number of themes that have been central to a bunch of these ideas that I want to touch on in a couple of ways. Uh, in fact, one of the issues about it that we'll touch on a little bit or examine a little bit is whether or not shellfish are simply starvation resources, which some archaeologists have argued that shellfish are resources that people would only eat in starvation situations, which on the Northwest coast would be in the late winter and early spring. And if you know much about the ethnography of shellfish use on the Northwest coast, you know that that's clearly in contradiction to that, but there's arguments that this is a starvation resource. And additionally, for a long time, during the 20th century, there were conceptual ideas about what a shell midden actually represented as a cultural deposit. So a little bit of history here for a moment. Uh, the first person, at least in Western science, who actually recognized shell middens as cultural deposits was almost certainly a Danish zoologist and paleontologist, a guy by the name of Jessup Steenstrup, who published a volume in 1837. And Steenstrup was actually really interested in fossil shelled beds along the Baltic, disposed along the Baltic shoreline. But he was also seeing shell midden deposits that were mostly Mesolithic in age, early Holocene shell midden deposits. I don't know if anybody listening tonight knows much about Danish archaeology, but what are now known as Ertebal shell middens. And Jessup, in talking about Steenstrup, in talking about them, presented arguments to tell the difference between fossil shellfish beds and these cultural deposits. And he made observations like that shellfish in cultural deposits are a mix of environmental habitats, whereas the fossil beds are a single habitat. He also noted that the size class distributions of the shellfish in the cultural deposits was not a natural distribution of size classes. And that's something we'll talk about again here shortly. And so for the 1830s, the guy was actually pretty sophisticated in terms of what he was seeing and understanding. After Steenstrup, Shellman deposits are among the first cultural deposits in coastal areas anywhere in the world. In most parts of the world on marine shorelines, Shellmans are identified in multiple places through the second half of the 19th century. Not a lot of real scientific work was done with them for the first 80 years or so that people were just noting their existence. James Swan, by the way, I think is the first person to have actually described the shell midden in Western Washington. And he does that in 1853 on Willapa Bay. Doesn't really investigate it, but he recognizes that it's a cultural deposit. In any event, most of the archaeology of shell middens for most of the 20th century in the United States, Canada, and even in Western Europe was heavily influenced by work that was being conducted in the Bay Area of California in the first 2 decades of the 20th century. And it was work being conducted by people like E.W. Gifford and Nels Nelson. And these guys were developed techniques for archaeologically sampling shellman deposits along San Francisco Bay. And they were interested in the contents of these deposits, and they took a rather simplistic approach that was treating the shell as a sediment. And so they would excavate a portion of a midden deposit, and then they would calculate the total weight of the shell and of the bone and of the charcoal and of rock and of artifacts and different materials to kind of look at the constituency of these things. And Gifford, in fact, wrote in 1914, 1916, described the methodology of how they did this. And he brought up the arguments that shell middens are refuse deposits and they're culturally amorphous, and the materials in them are rather homogeneously scattered within them in their makeup. And well, he argued that, and Nels and these other early researchers argued that, it's clear from Gifford's writing that he didn't really believe that to be so, because in some of his accounts of how to sample one of these deposits, he warns the reader to avoid atypical deposits in the sampling. And it's clear that Gifford understands that the atypical deposits that he wants you to avoid when you sample are cultural features. There are haars, there are pits, there are other types of structures in situ features in the midden. And so he understood that they were not homogeneous or culturally amorphous. But that's what he argued. And people started doing that in other parts of the world. Harlan Smith was doing that here in Washington, just very early in the 20th century. And other people started picking up this approach in Western Europe and in Eastern North America. Kind of fades away by the 20s and 30s. Nobody's really doing it much. And then after World War II, when we really begin to see modern archaeology spreading in many parts of North America, in the late 1940s, 1950s, even into the early 1960s, researchers in California schools in the Bay Area and in UCLA published a series of papers in journals following up on the Gifford-Nelson technique, internally homogeneous and uniformly spread around it. And they published a number of papers that they thought were methodological. And it was about finding how much is the optimal size sample to sample a shell midden deposit. But truthfully speaking, while they kept saying optimal, what they meant was minimal. How much of this do I actually have to look at? And do I really have to look at a lot of it? And something that really striking to me that was lost on these people for the better part of 20 years is, to the extent that the deposit really is culturally amorphous and homogeneous in its internal contents, sample size is not really very important, because a 2-pound sample and a 2-ton sample are probably going to show you pretty much the same thing if it really is homogeneous. But the point is, it's really not homogeneous. And that's something I want to show. Okay. So we have shell middens. And this is a term that I think, and certainly Western Washington archaeologists are very familiar with. And it's a term that lacks a precise definition. Midden means it's an anthropogenic deposit, and a shell midden is an anthropogenic deposit that has lots of shell in it. And the way the term has been used for a lot of the 20th century, it comes with the implied connotation that it's shell over a certain density. It's not any deposit that has 1 or 2 pieces of shell. It's a deposit that has a relatively high density of shell, although nobody has ever actually proposed a density number for how much shell do you have to really make it a shell midden. Okay. And again, traditional ideas, we have talked about this already. Shellfish is a starvation resource, shell as a dump. Okay. All right, let's look at the critters. And the animals I'm going to show you now, or classes of animals, are really derived from Ozette. And the truth of the matter is that the marine invertebrate faunas on the outer coast, where wave energy is very high, are different from the Puget Sound Basin. And some of these animals have very low ubiquity, as ecologists would say, and occur in both places. They occur on the outer coast and in Puget Sound. Others are pretty specific to just one wave energy regime or another. And when I say shellfish, I'm talking about marine invertebrates. And at OZET, where 90 varieties of marine invertebrates were identified, and that's in part because of a very, very large sample. But even small samples of middens in Western Washington can have 30 or 40 different types of marine invertebrates in them. And predominantly, we're talking about mollusks and bivalves, clams, mussels, critters like that, univalves or gastropods, marine snails, limpets, those kind of critters, chitons. And if you're not from Western Washington or you're not familiar with saltwater, you may not be familiar with these critters. They look a little bit like big marine slugs. I'll show you a couple of pictures in a minute. They're kind of related to limpets and abalones and critters like that. But chitons are common in these middens, evidence of chitons. Scaphopods, there's only really one scaphopod that we need to talk about here, and that's Dentalium. Also a tusk shell. I'll show you some pictures. Cephalopods, octopus and squid. We don't really think of them as shellfish, but they're mollusks, and we can see evidence of them in sites. Beyond the mollusks, and that's mostly what we're talking about, arthropods include barnacles and crabs, and echinoids, sea urchins. And there are physical evidence of all of these things in large marine middens in Western Washington. Okay, first off, I'll show you some of the more common and abundant ones. California mussel, sometimes called sea mussel, and these animals live in these large aggregated masses on rocks. And these are what marine ecologists call epifauna. That is, they don't live buried in the sediment. They live attached to rocks and other masses. You can see here, these mussels have what are called biseal threads. They can aggregate on the rocks and aggregate to each other in these very large masses of mussel. They're predominantly mussel, but if we looked at them real close, we'd see there's barnacle in there, and we'd also see that there's a large number of small carnivorous gastropods, dog whelks, dire whelks, things like that, that actually eat the mussels, drill into the mussels, and they're all mixed up in that mass. This is the dominant mussel on the outer coast of Oregon, Washington, and British Columbia, actually. Okay, we also have Mytilus edulis, the blue mussel, and this is the bay mussel, as opposed to the sea mussel. The California mussel is the sea mussel. Mytilus edulis occurs all through the northern hemisphere. This animal is on the east coast of North America and in Europe. This is the edible mussel. If you like Pen Cove mussels, this is the animal we're talking about. And this also aggregated by biseal threads, but this is a much smaller animal with a much thinner shell. It's not very robust like the California mussel is. So this is the low wave energy animal. The California mussel is the high wave energy animal. Okay, then also very, very common, and these have a much lower ubiquity, which means they're not really tied to a single environment. We have these on the outer coast and all over Puget Sound. This is the little neck clam, Protothacus domenia, and I will tell people also, you need to learn a bit about the shellfish. You can see that very clearly. And the shellfish taxonomic people keep changing the names. This animal, very common in middens, is now newer guides call this Lacomas domenia, not Protothacus domenia, but it's the little neck clam. It's the same one. The butter clam, Saxodomus giganteus. I don't think they've changed this name yet. These are also very common, both inside in Puget Sound and in the outer coast. They like slightly different substrates in the intertidal zone, but they're also very widespread. Horse clams. There's actually two different horse clams in Western Washington. This one is Traces capex. There's also Traces natali. These are the largest clams that show up regularly in Western Washington shell middens. Evidence of geoducks has been reported in some places, but they're not very common. And geoducks are not an intertidal shellfish, they're subtidal. And how much Northwest Coast people free dove to get marine invertebrates is a subject of some debate, and probably wasn't much at all. Okay, univalves, marine snails. There's 30 or 40 different types that can occur in these sites. I've just thrown out a couple of things here that are very, very common and widespread. This on the left, these are Sitka periwinkles. These are quite small. These things are like half an inch in size. Extremely common on the outside of the Washington coast, not very common on the inside. Frilled dog winkles here are very common all over the region, inside and outside. These are some of these carnivorous snails that we find in the big mussel packs on the outer coast. And actually, they attack bay mussels on the inside as well. Very common all over. Okay, chitons. Cryptochiton stellari is this thing here. So sorry, I don't have a scale, but this is the biggest chiton in the region. And chitons can be 12, 15 inches across. They have a series of plates inside of them, and I'll show you in a couple of minutes what that looks like. So this animal is both in high energy and low wave energy animals. The black Katy chiton, Catarrhina tunicata, is very common in high wave energy settings. If you go out to Cape Flattery or Cape Alava, there's some places in the San Juans, the Cattle Point, where there's high wave energy. You could see them there too. But it's not nearly as ubiquitous as the Stellaris chitons are. In fact, if any of you talk to native people and you hear native people talking about boots as a kind of chiton, that's Cryptochiton stellari. That is often called a boot or boot chiton. Okay, scaphopods, dentalium. Dentalium kind of looks like a univalve, but it really isn't. It's a separate critter, and these are subtidal also. They don't occur in the intertidal zone. Places where they do occur naturally can be in 30 to 40 fathoms of water. And honestly, I'm not going to take the time here to go through the apparatus that people use to collect these things on the outer coast prehistorically. But it's really an amazing quandary because the technology that was used to acquire these things is unlike any other piece of Northwest Coast technology. And you could understand how you might come up with the contraption if you knew where the shells were and wanted to get them, but you can't even sample to find where the shells are until you have this piece of equipment. So it's a strange situation, but people were collecting this stuff, and this stuff was traded widely in North America. Okay, octopus, cephalopods, North Pacific octopus. And also we have some kind of squid represented at Ozette also that hasn't been keyed out. And if you're looking at this picture and you're wondering, like, so what preserves out of an octopus? And what preserves are the beaks. The one on the right, this is an octopus beak. This one here is some kind of a squid. We were unable to figure out. These things are about 2 inches across. It kind of depends on the size of the octopus, how big they are. And they are made out of a material that's kind of like your fingernail. And I have to tell you that we have a couple hundred of these from Ozette. And Ozette is the only site in Washington where they have been reported. And to me, it's not possible to imagine that that's the only place that they were being used. I think we have them at Ozette because everything was water recovered through water screening. And these things are probably really hard to see in dry shell midden deposits when you're dry screening, but they're probably there. Okay, crabs. Ozette has 4 different types of crabs represented. It's not unusual for at least 2 or 3 kinds of crabs to be represented in a site. Unfortunately, the way that most crabs are butchered to be consumed leaves only little tiny pieces that are hard to be identify or work with, but the claw tips on the big pincers are pretty dense. And these things can be recovered, will be recovered in shell midden deposits, and can be keyed to species on the basis of just these dense hard parts. And that's about the only part you're really going to see in a shell midden that is going to be identifiable to taxa. Barnacles. We have 3 different large groups of barnacles that show up in sites in the region. Up here, these are examples of what are usually called sessile barnacles or acorn barnacles. They're barnacles that live on rocks or on pier pilings and stuff like that. There's at least 8 or 10 different species in Western Washington, some just on the inside, some just on the outside, some in both. And honestly, they're really hard to keep as species if you just have the archaeological, if you have the walls of the barnacle. Sometimes if you have the little head plates from the animal, you can key some of them out, but they're hard to key out. They really are. Down here in the bottom, we have gooseneck barnacles. The plates of the gooseneck barnacles do show up in middens. There are what are called pelagic goosenecks, which you see here, and these are barnacles that attach themselves to flotsam, pieces of wood or plastic now, and live on the ocean, but then these things wash in, and when they wash in, and when they're fresh, they're still alive and can be consumed. There's also a gooseneck barnacle in Western Washington that actually lives attached to rocks, similar in appearance. And then these things here, which we only have seen in archaeological sites out on the northwestern Olympic Peninsula, these are whale barnacles. This particular one here is a barnacle from a humpback whale. Whale barnacles are species, host specific. The ones from gray whales are different from the humpbacks. And these things come into the site when people capture whales or use stranded whales. And so we do see whale barnacles on the outer coast. We really don't see them on the inner coast. Okay, and sea urchins. Sea urchins, there are 3 different kinds of sea urchins in Western Washington. There's green sea urchin, purple sea urchin, and red sea urchin. They're really not intertidal, they're shallow subtidal, but there are many places in Washington where on a good low tide you can find them in tide pools. And we even know that the red sea urchin, which are the biggest ones, that Northwest Coast people had kind of a blunt spear that they could hit these things in less than 10 feet of water when on low tides and crash into the shell and then recover them that way. So these occur quite often. And for if anybody here listening has seen layers in some shell midden sites in Western Washington and the San Juans and central Puget Sound, you can see big massive layers of crushed sea urchin test very prominently. And in some of those, if you were to screen some of that sea urchin test off, in some places you'd find that there's a lot of herring bones in it. Yeah. And the sea urchin and the herring are spring resources. So sites that have those kind of layers in them, you're looking at a springtime activity. Okay, to make sense out of these things, we need some kind of a functional model for why shellfish are even in these deposits. And so as part of my doctoral dissertation, after reviewing the ethnographic descriptions of shellfish use on the Northwest Coast, I put together basically a functional classification for why different taxa are in these deposits. And I'll tell you, first off, I'll go through these types for you. The types are not mutually exclusive. Certain taxa can be representative of several types. But basically, here, just to go through these quickly, and then I'll show you some pictures and examples. The types that I put together are, okay, first off, primary prey. And primary prey species are species when a shellfish collector is going out in his mind. That's what he's thinking he's going for. He's going for butter clams. He's going for California mussels. He's going for steamer clams. He has particular target prey in mind. Secondary prey are species that he's probably not thinking that that's what he's going for, but if he runs into them while he's looking for his butter clams or steamer clams, and in some places on the outer coast, he may encounter white sand clams, which are one of the larger macomas. And if they're large, they're going to keep them just because there's meat there and they've encountered it. But they're not going out for white sand clam. They're going out for butter clams or steamer clams. But when they encounter them, if they're large enough, they hang on to them. Okay, fish bait. Certain amount of the protein from bivalves and other marine invertebrates, we know ethnographically people were collecting not to consume themselves, but to use as bait for fishing. And among other things, we know that small octopus and squid were a favored bait for halibut fishermen. And so they're acquiring some of those small octopus and squid to not for their own consumption, although they may well have been eating them also, but in part they're using them for fish bait. Okay, there is a limited sketchy information that suggests that some of these marine invertebrates may have had medicinal properties, although to my knowledge, nobody seems to know very much about this other than some traditional elders. The only example I can sort of give you is that I was told by traditional elders in Neah Bay in the 1970s that the purple hinge rock scallop, and I don't know if people know what a purple hinge rock scallop is. It's another bivalve that we have here in Washington. And I was told that the elders said that you could take some of the shell of purple hinge rock scallop, grind it up into a powder, mix it with water and certain plant botanical materials that were not described to be specifically, and that they made a poultice out of it. And it was used on small skin wounds, cuts, and things like that, and sores. And then it had a healing properties to it. There were probably other medicinal things about some marine invertebrates, and it's just not a subject we know much about. Okay, decorative, symbolic, and ceremonial things. There are a number of shellfish species, and now I'm thinking about things like dentalium or abalone, red turban opercula, which are inlays that have a lot of nacreous color, iridescent color, uh, olive shells. People may be aware of olive shell beads and necklaces that people used. All of those things are a class unto themselves. Then raw materials, tool stock. And the raw materials are almost exclusively in Western Washington, either big California mussel shells for which you can make knives and projectile points and other cutting blades out of, or large horse clam shells, which were used as bowls or containers. That's pretty much the range of tool stock. Okay, and then at the end, I have inadvertents and incidentals. And inadvertents are taxa that arrive in the site as part of, as a byproduct to another activity. And I've already shown you one good example of that, and that's whale barnacles. We don't actually know whether whale barnacles were consumed also, but we know that big slabs of whale meat were coming off the beach and coming up into houses. And if those slabs had barnacles in them, the barnacles came along with them. And I can give you one other example from Ozette that is also, I think, a really good example of inadvertence. In a sample of representing more than 160,000 animals, so we'll talk about NASP in a moment, I have some taxa where I only have 2 or 3, or just a tiny amount, well, 1/100% or less. And in the Ozette sample, there are 5 or 6 examples of a very small marine snail that is free swimming subtidal. It's not something you would encounter in the intertidal zone. It's a deeper water marine snail. And we had a few of them that came in, and I couldn't understand why we had them. They're not big enough to be a food resource of any particular way, and yet we were seeing them. And I was talking with a marine ecologist. In those days, the marine ecologist at Peninsula College in Port Angeles was a guy by the name of Art Farrell, who helped me in a lot of ways. And when I talked to Art, I said, well, why do I have a few of these things? He looked at them and he laughed and he said, some of the fish that macaws take regularly, like Pacific cod, and some of the sculpins, eat these snails. And if a macaw caught a big cabezon sculpin or a Pacific cod or a tom cod, shortly after he'd consumed a couple of these snails and hadn't digested them yet, the snails came into the site in the fish's gut. And then when the fish was gutted, they were deposited into the midden. So we see evidence of that kind of stuff too. And then finally, there's incidentals, which is just idiosyncratic behavior. Somebody picked up a pretty shell because he thought it was a pretty shell. Uh, I would tell you just on that level as well, just as a thought here, I would tell you that a lot of archaeologists for a long time, if they excavated in a site and they found something that was obviously an artifact, was obviously manufactured, but it didn't make functional sense, people said, "Oh, it's a ceremonial object," and it was that with these intact houses, with everything then completely intact houses on them. I don't know who started it, but when we find something weird on the house floor in one of the house floor in one of the nuclear family areas on the house floors that I was at, the excavator would go, "Damn kids," which I think is a better explanation than ceremonial part of the time. Anyway, give you some examples of what some of the stuff looks like. For the decorative and ceremonial stuff, I think everybody's seen probably dentalium. Uh, and actually, as a side here, if I've got some Eastern Washington folks here tonight, I don't know. Uh, the Grant County PUD bought a large collection of artifacts from a collector in Grant County, who was active in the early part of the 20th century, and he has a bunch of dentalium that's been incised as patterns on them. I've never seen that in Western Washington. I think that that's something that was done to these things after they were traded to Eastern Washington. We have clamshell beads, abalone beads, disc beads, olivella shell beads. And olivella shell beads, you may know, occur up and down the Pacific coast of the United States, and from British Columbia up into Canada and down into the Gulf of Mexico, not Gulf of Mexico, Lower California. And the tops are cut off, and these are beads. If you go to Nia Bay, you can see Macaw people wearing these widely today. And these things were traded east of the mountains. We don't know how early, but I can tell you that there are olivella shell beads at Marmas Rock Shelter underneath the Mazama ash. And so those are olivella shell beads that came to Eastern Washington almost 7,000 years ago. And I would also tell you, because it's not widely recognized, olivella shell beads show up occasionally in sites in Puget Sound. I think there's some from Old Man House over on the Kitsap Peninsula. And even on the Kitsap Peninsula, this is a trade item because olivellas, purple olive shells, only live out on outer coast beaches that are fine sand beaches where the waves pound. You find them in the same place, kind of beaches where people get razor clams. So even when they show up on the Kitsap Peninsula, they're a trade item. They don't come from Puget Sound. They come from the outer coast. Ground mussel shell tools. This is what most mussel shell is used for in terms of tool stock. There are knives where they're on a hafted handle, or it's a whole valve with a bark strip on them. Other types of hole valves are set up like this or in wooden handles. We do see harpoon blades, prehistoric whaling from Macaws and Quilly, which were done with ground mussel shell blades. And we also see small numbers of ground mussel shell look like projectile points. And I will tell you that you can put a pretty sharp edge on a piece of ground mussel shell, on these big California mussels, but it's a pretty friable material, and it has a relatively narrow angle of attack for getting into it or putting material into it. So whether these things are really arrowheads for real hunting purposes or whether they're made for some other purposes is really not clear. Personally, I have some doubts about how effective they would be on the ends of arrows, but we do see these things showing up in sites. Okay, I'm just going to give you some quick background on Cape Alava first, a little bit about the site, and then we'll start looking at the shellfish collection from the site. For those of you who've never been there or don't know much about it, Cape Alava is northwest of Lake Ozette. It's about 20 miles south of Cape Flattery. The dot here, the red dot, is about where the site is located. The old village was actually the whole point, and off on these offshore islands as well. And just real quickly, this all I really want to point out to you in this graphic is there's a range of different intertidal habitats for shellfish, because we're going to come back to this in a bit. But if we look at this here real clearly, Mytilus californianus, the Mytella is a gooseneck barnacle. These are on all the outer rock locations, on the outer part of the wave cut platform. That's where you see the high wave energy places. Protothacus, butter clams, steamer clams, like these sandy, gravelly beaches. We have a series of those here and small pocket ones after that. Acmean litorina, this is limpets and the periwinkles. They like to be on small rocky headlands. You could see them at just certain fixed places, but they're not widespread. And then Mytilus edulis. Right here at the mouth of the Ozette River, there's a place where blue mussel, bay mussel, lives. It's the only place in this whole area that has to do with salinity and the fresh water coming in. So California mussel is over the whole place. This location right here at the mouth of the river is the only place that has blue mussel. And tuck that in the back of your head, because we'll make an observation about that here in a bit also. If you want to see what it looks like, and actually, I should point that out. Here is Ozette Island right here. And like I said, the site is here. The excavation is right there. Here's Ozette Island on a minus tide, but not a deep minus tide. This is probably a minus 1 foot, foot and a half tide. Some of the tides in the late spring can be 2.5 foot tides. But here you have a big wave cut platform. And Ozette Island, the big mussels are out on the outer edge of this area. Okay, a little bit north of where where the excavation is, these rocky headlands, like in the foreground and the back, where the limpets and the periwinkles are, and then we have sandy, gravelly pocket beaches where butters and steamers can be collected. And then this is the Sand Point. This is the beach 3 miles south of Ozette, and this is a razor clam beach, and also a place where olivella shells can be obtained. Okay, just quickly about the site. This is a photographic cable lava in the 1890s. And just real quickly, I just want to point out a couple of things. If you look here, you could see the houses along the beach are a mix of traditional shed roof architecture, like this house here, and this one here, and these here. These are traditional shed roof Deccan style plank houses. But there's also European style gable roof houses here with horizontal planking. And in fact, here's a shed roof house that has a frame door on it. So there's a real mix of technologies in the 1880s, 1890s. Ozette people were here until about 1910, 1920. And the other thing that I would point out to you here is there's no trees on the hillside at this time. Wood is a major building material for Ozette people, and it's also your principal fuel for heating. And they just took all the trees away, which is part of the reason that slides were a big issue. Here's a picture of the excavations in the 1970s. This is the archaeologist camp. The slide covered this area. We're right at the south end of the slide right there. And this is where all the excavations were occurring between 1970 and 1981. Just to give you a couple of pictures, and hopefully people have seen some of the stuff before. This is in situ, east wall of house 2, still in place, excavating with water. And you can see these hard platforms were cut into the slope of the hillside. This is the upslope side. And so the lower part of the wall was protected by the cut of the bank, and the slide sheared it in place. So everything above the tops of these stakes was sheared by the slide. And this here piece, this is a rafter support. And you can see it was snapped off and broken by the force of that slide. So you can really see some of the energy that was coming down the hill. Okay, and here I just want to show you, this is the bottom of the slide that covered all this stuff. And here's the underlying deposits underneath it, and it's a shell midden. with cordage and wood and the organic preservation, but basically it's a shell midden deposit. Okay, a few more quick things to orient you, and then we'll get back into the actual collection. This is a stratigraphic cross-section of the deposits in what we call the B70 area, and that's the area that was excavated for 11 years. And in this profile, Unit 2, Unit 4, and Unit 6 are all clay slides, or all clay lobes from big slides that came down the hill. Unit 1 is late historic. It's probably the late 1880s, 1890s, or late 20th century, the last bit of occupation there. Unit 3 had an early historic house in it, but we don't know that much about it because in 1970, when they didn't know how long they'd be there or what they were looking at, this house was blown away with fire hoses to get down to this house, House 1. Unit 4, what we call Unit 5, is defined initially as the interval between the beginning and the abandonment of House 1. And in this image here, you can see that there's two houses behind House 1 that fall within that interval. There's House 5 that didn't last very long, and then there's House 2 over that. And the big Unit 4 slide is the slide that comes down the hill in 1700 and preserves all the organics in these houses. And just one last thing for you here. We don't know too much about it. These stuff are radiocarbon dated at about 300, 350, and we think this interval is about 100 years. Underneath Unit 6, they put a deep test pit in late in the 1970s, and they found Unit 7, which is radiocarbon dated at about 800 years, and it's also preserved organics. It has basketry, cordage, and all this stuff that's up in there. And we know in other parts of our Rosette it's 2,000 years old, so who knows how many layers in between clay deposits are represented here. Okay, now I'm going to give you an aerial view of those slices so you can get some sense of the internal space. Here's House 1. This is the house that was discovered in 1970 when the west wall of this slumped off onto the beach when in a storm, winter storm in January of 1970 that led to the discovery that this portion of the site was waterlogged. Just behind House 1 is House 5. And this house was built shortly after House 1 was built. And we know in an occupation interval that was probably not more than a decade or two at the very most, this house was kind of in a low spot, and small slides penetrated the floor and made a mess in here several times in the early history of this house. And after maybe the third or fourth time they had to clean it up, they just said, screw it. And they abandoned this location and salvaged most of the stuff they had there. So there's not a whole lot of artifacts, not a lot of planks, because it was purposely abandoned. Okay, a little while later into Cultural Unit 5, another house is built just north of House 1. This house has its long axis perpendicular rather than parallel to the bank. And House 3 persists for a while, and during this interval, another slide comes down the hill and settles back in here, penetrates in House 1 a little bit, but it's not a big issue. But it raises the base level. It adds about 30 centimeters more gradient back in here, and behind House 1. And then somebody, maybe even the House 5 people, we don't know, comes back in now that there's better drainage and builds another house there. So that's what you have in the B70 area. And just to summarize, we have 3 complete longhouses, the exterior deposits around them, and perhaps 25 or 30% of a 4th house. And just as importantly, House 5 was abandoned without a catastrophe. People took most of their stuff. House 1, House 2, and House 3 were covered by the slide and ended catastrophically. Okay, one last thing, and now we get to shells. Just to understand, and I'm going to show you some other stuff later that relates to it. At Rosette, we have a couple of different spatial ideas to organize understanding space on the house floors. And these globular things are fire hearths. we know that from ethnographic sources that each nuclear family area, and probably everybody who lived in this house, were related to the house owner. And usually it's the house owner, his brothers and adult sons, wives marry out. And so each one of these is a nuclear family area. They're not necessarily all contemporaneous. This house stood for almost 100 years, but we see that many areas around them where we would expect to see replicated domestic stuff in each one. And then there's activity zones that overlay this. And there's basically a bench zone because there's benches all around the house floor where people don't walk, but garbage gets swept. And then a hearth zone, and then a center floor area where various economic processing activities, social activities, ceremonial activities all occur out in the middle of the floor. Okay, so now let's look at the Ozette shellfish collection. What do we actually have here? Okay, and I'm going to show you a couple of different summaries of the Ozette collection. And we could quantify it different ways. And I'm going to show you NISP, just the number of identified specimens, then an MNI, minimum number of individuals, and then a category that we call live meat weight, just calculate, well, how much meat do we think we're talking about? And some of you, if you're familiar with reports on shellfish analysis, will say, well, wait a second, there's another way that this stuff could be summarized also, and that's by weight. Not how many pieces, but, well, I have so many pounds of California mussel and so many pounds of steamer clam or butter clam. And I'm going to tell you, if you're treating the shell as a sediment, there's reasons why you might want to use it by weight. But if you actually want to talk about animals, characterizing what you got by weight is an almost completely useless exercise. There's almost nothing you can do with that information. And by the way, if you're thinking about doing something and you're thinking about doing something with post-depositional effects where the weight is meaningful, consider this. Calcium carbonate, what marine shells are made of, is not impervious to water. And in wet environments like we have here in Western Washington, in the wintertime, shells will absorb water if they're in a matrix that's wet. And so if you're actually interested in the weight of the shells you recover, dry them out first. Because if you don't dry them out first, you're measuring an unknown fraction of water that probably varies within the sample that you're weighing. And it's just, I would argue there's not much point in doing it. But certainly if you want to talk about animals. Okay, the NISP for the Ozette sample is 306,456 pieces of identified shell. And we made a bunch of observations about the individual pieces in addition to taxon, how complete it was, size, a number of other things I'll talk about here in a minute. But if you look at this real briefly, California mussel, blue mussel, Milocedulus means it's one of those two, but I can't tell which. But this is almost 65% of the entire sample is bivalves. And they're all the big components in terms of pieces. And the big bivalves, there's not that many big, but really important bivalves and middens in Western Washington. When I showed you before, when I showed the tax of the mussels, butter clams, steamer clams, horse clams, cockles, there's a few other things, but there's really not a lot. Univalves are 18, 20, 24% are univalves. And those Sitka periwinkles are 18 of the 24%. There's gobs of them. Chitons, all chitons are 6%, all crabs are 1%. Mitella, that's another kind of barnacle, gooseneck barnacle. Cephalopods are less than 1%. They don't even show up here. Okay, let's now look at minimum numbers of individuals and see what the same sample looks like. And so the 306,000 pieces represents around 160,400 animals minimum. MNI is not actually an estimate of the total number. It's trying to identify a threshold. It must be at least this much. And you can see here bivalves are still 50 something percent. Littorina is now 34%. And all of these other categories, all crabs, octopuses, and whale barnacles together are 1%. Chitons are 2%. Barnacles are 3%. So just going from NISP to MNI changes what the total looks like dramatically. And before I show you the live mean weight, I want to talk to you a little bit about how you do MNI with shellfish. Some types of shellfish work quite well. Other types are really a problem. Okay, first off, let's talk about bivalves. And I've already told you the bulk of what you're going to find in most any min around here are going to be bivalves. And to estimate how many animals of any particular type, we're going to use a technique that faunal analysts use with vertebrates also, and it's what's called paired element analysis. And a faunal analyst working with deer bones, for example, would look at all of the bones they have from deer once they figure out how many were deer, and they look for a paired element like a humerus or a tibia or a femur, something that you have a right and a left of in the skeleton. And if they figured they had more femurs than anything else, they count all the femurs and they'd cite them, which ones are rights and which ones are lefts. And if you have 15 rights and 20 lefts, you have to have at least 20 animals. And so that's where the minimum number estimate comes from. Now, faunal analysts and biologists use certain terms for orienting within the directions within the body. And I don't know how many of you here tonight have done any type of faunal analysis or with skeletons, but the deal with bivalves is there are conventions for turning those terms that we use for vertebrates and applying them to bivalves. And I'm going to show you basically how that works. And we're looking at the interior now, the inside of a veneride clam. This could be a steamer or a butter, but this works for any kind of clam, any type of mollusk, any type of bivalve, excuse me, mussels, oysters, stuff like that. Okay, and as we look at it, there's a number of landforms or sculptures, landscape features on it. And as we look at it, at the inside, along the edge that articulates with the other shell, there's an area where there's hinged teeth and sockets. There's holes and little ridges that stick up that articulate with the other half of the bivalve so that the clam opens and closes. And if you steam clams sometime and they don't open completely, you can see how it opens on that edge. And so you got that tooth. On the outside of the shell tends to come to a point right around near where those teeth are. That's called an umbo. Some people call it a beak. And then from the umbo back across the top of the shell, there's a ligament. And that's that leathery material, kind of almost like your fingernail that the hinge swings on. And again, when you steam clams, that's what opens up. Okay. The shellfish guys, trying to use anatomical terms, equate that ligament there with your spine, with the spine of a vertebrate. And so the top of the shell, and this thing, the margin of the shell where that ligament is the anterior side of the shell, is the dorsal side, excuse me. Dorsal means your backbone, you know, dorsal fins and sharks and whales. So this is the dorsal side. And opposite the dorsal side, which is the margin that opens up the most on a clam, is the ventral side. Ventral means belly, dorsal means back. So this is the back, this is the belly, and that means the other two directions must be anterior and posterior. Anterior means toward the head, posterior means toward the butt. And when we look at the interior of any kind of clam or mussel, there's a line here near the bottom that runs around the interior. That's called a paleo line. And I'll show you some other examples. You'll see them, or, you know, spend some time on the beach, look at some shells. You'll see these things. This is a paleo line, and you'll notice on one side of the animal only, there's a concavity in the paleo line. It's called a paleo sinus. For those of you who dig and eat clams and know a little bit about the anatomy of clams, you know that a clam has a foot that it can dig with. The foot comes out here, and this paleo sinus, if you open up your clam before you eat it, you'll know that there's a tube or two tubes that come out of its body this way and stick out down the end. Excuse me. And that line up with the paleo sinus. That's the clam's anus. It's the clam's organ of excretion. You know, everybody's got one. And so obviously the paleo sinus is posterior. And the side that doesn't have the paleo sinus is anterior. So now we know dorsal, ventral, anterior, posterior. And classically, when they train people, they say, okay, so what you want to do is you pick up the valve that you want to know whether it's a right or a left. And you hold it in front of you with the dorsal side up and the anterior side facing away from you, looking in the same direction that you're looking. And when you hold the valve that way, the anterior side of the shell tells you whether it's a right or a left. If the anterior side is on the right, it's a right. If the anterior side is on the left, it's on the left. Now, I'm hoping everybody's following this. It's a little complicated, but actually there's a cheater way to tell. It's much simpler after I explain to you the way they teach it. If you look at any kind of a bivalve here, and you look at where the hinge teeth are and its relationship to the ligament. If the hinge teeth, when you look at the interior, are to the left, if they're at the left end of the ligament, it's a right. If the hinge teeth are here at the right end of the ligament, it's a left. And so people are not real impressed as a party trick, but this is how we tell the difference right and left clams. And just to show you a couple of examples, this is another one. This one has the paleo sinus on that side, so this is a left. This actually, I saw this. I got this out of Google Images. Here's a mussel. Could be California mussel, and actually the guy who did it screwed it up a little bit because that's not the abductor scar. That's the paleo sinus right there. And here's the ligament form right there. The beak is there, so this is a left also. This is a tropical scallop. They're weird. We don't need to worry about them. But this left-right thing would give you a basis for deciding how many of each bivalve taxa you had. You know, if you go through all of the butter clams you have and you have 28 lefts and 21 rights, you have a minimum of 28 animals. Now, if you want to be more labor intensive, you can get a better number for how many you have. And I did this at OZ, and that is we made size class templates. And you do this from spending some time on the beach and finding specimens that are the right size. And this is my templates for blue mussel. There's a 3 centimeter, a 4 centimeter, a 5 centimeter, a 6 centimeter, a 7 centimeter. These are not real time consuming to put together. And by the way, if there's anybody out there who is interested in using this technique and wants to use templates, I don't have them for all, but I have butter steamers, horse clams. I'll give you, I'll make you set that, or you can just do it, make your own on the beach for whatever you want. But these templates allow you to separate into size classes before you do your left-right splits. And you can see there's a left-right for each one. And if you just do left-right, but you don't separate them by size, you'll get one number. If you take the time to break them up into size classes, you'll get a much larger number of what that minimum actually is. And while this does look time consuming, I'll tell you in practice, these templates will let you drop incomplete pieces into size classes. The densest part of most bivalves is the area around the hinge. And just that end of these size classes will let you take small hinge fragments and place them into size classes. And I'll show you here shortly that if you have the size class information, you can integrate it with other types of information to see some pretty interesting dynamics. Okay, so size classes is a way to make your MNI more accurate than just simply citing them without separating the size classes out. Okay, for univalves, and a lot of the univalves here on the Northwest Coast are pretty stout things. They don't break real easily. So if you have whole individuals, obviously, we count them as whole individuals. For fragments of univalves, and this is Thyas again, the only part that's really diagnostic for counting, if you have fragments, is the spire, the top there, and it's not paired, but there's one per animal. If you have other portions of the shell that are broken up, you can't really count them, but you can count complete animals and you can count spires and come up with an MNI that way. Chitons, told you that there's a bunch of 8-segmented shells. This is Cryptochiton stellari. This is the boot chiton. Other chitons have similar arrangements, and inside this critter are 8 pieces of calcium carbonate. And if we looked at the black Cadies or other kinds of chitons, it's a similar situation. And when you look at these pieces, this is the head plate here. It's unique and distinctive. This is the tail plate. It's also unique and distinctive. And then there are 6 body plates here. And actually, if you really wanted to, you could probably even make the case that each one of those 6 are distinctive. When we did this at Rosette, we classified these things in 3 categories. We counted obvious head plates, we counted obvious tail plates, and we counted body plates, the 6 body plates. And when you count them that way, when you're done, then you have 3 numbers to pick from to see which number is largest. You can see what your total of head plates are. You can see what your total of tail plates are. And you can total all your body plates and divide that by 6 because there's 6 per animal. And then you have 3 numbers to choose from. And obviously the biggest of those 3 numbers is the MNI for that species. Okay, cephalopods, octopuses. And the truth of the matter is that the 2 parts of the beak look different. And these are the 2 things you're looking for here. They call this an upper and that a lower. Honestly, when I look at an octopus, it's not clear to me which one is upper or lower. But this is another paired element thing. You count all of the uppers, all of the lowers, and take the larger number, and that's your MNI value. Okay, a few other things just for MNI, and these are mostly to problem children. Crabs, I told you before, are usually finely crushed and you don't get a lot of whole crab shell, but the pincers in crabs are thick enough that you are going to see those in shell midden deposits. And there again, it's a paired element. I don't have a good picture here too, but if you get yourself a comparative sample, you can see that there's 2 elements. They're paired much like an octopus beak, and count each group separately and take the larger number. Barnacles and sea urchins are really pretty problematic in this regard. There are ways for some types of barnacles and some types of sea urchin to pull small things like some of the head plates, and some types of barnacles can be keyed. And you know, and if you got all of the ones for a particular species, and I think there's 4 per animal, you could divide that out by 4. Honestly, somebody gave a paper at the Northwest meetings about 10 years ago. I think it was someone from Bellingham, Western, one of Sarah's students, keying barnacles that way. It's extremely tedious, and you're only going to get a certain amount of information from it. You're really not going to get a good quantitative things. So, I mean, honestly, for the ozette stuff, for barnacles and sea urchins, we just weighed them and totaled the weights, and there was really not much else you could do with them. Okay, and so here's the last one. Now, those are the MNIs. Once you have MNIs, which I just showed you, then you can calculate meat weights by, again, working with live specimens. Just take them off the beach, collect different types. You know the size ranges, so you can pick sizes. You can calculate meat weights. You can produce meat. And what I really want to show you with these things, and I think it's actually on the next one, is okay. So here's for some varieties when they knows that stuff, the NISP proportion, the MNI proportion, and the live meat weight proportion. And so for all bivalves, 65% of all pieces, 55% of all animals, but only about 46% of all meat represented. Same thing with mussels, which are the biggest constituent in the bivalves, 43%, 38%, 28%, dropping. Univalves, 24% of the pieces, 40% of the MNI, but that's mostly these periwinkles. I showed you before, there's gobs of periwinkles, but the periwinkles are tiny. They're like half an inch. And so, well, periwinkles are 18% of the NISP, and a third of all the MNI. They're only about 1% of the meat. And similarly, larger things with bodies, chitons are only 6% of the NISP, 2% of the animals, but they're almost a quarter of all the meat, just because they're larger body sizes. And the cephalopods, less than 1% of the NISP, 1% of the MNI, and at least 17% of the meat. So body sizes becomes a big factor here in understanding what these things look like. Okay, let's talk a little bit about shellfish collecting behavior that we can see in this stuff. And one of the things that we can tell from shellfish is seasonality. And for seasonality, we're going to work mostly with bivalves. And actually, some bivalves are better to work with than others. This is a cross-section of a bivalve shell. And you can see here, this part is magnified a little bit. It's a series of light material that's been laid down with dark bands. And shellfish bivalves metabolate calcium carbonate. And they also continue to add shell size, body mass, and shell size for as long as they live. So a really large one is a really old one. They don't grow as fast once they reach sexual maturity, because then they're putting a lot of energy into reproduction, but they continue to grow. And because they're cold-blooded in cold parts of the world, which we qualify here, where we have distinct seasons in wintertime, the rate at which they deposit new calcium carbonate, which they grow on this end, grows from the outer end on the ventral surface and the ventral edge. They deposit material growing out there, and the rate at which they deposit that material is affected by temperature. There's other variables, but for our purposes now, we can just think about temperature. And at the coldest time of the year, which for us is usually like in January sometime, the coldest time of the year, it gets cold enough that their metabolism shuts down enough that they're not producing more shell material. And when that happens, you get a dark band forming on that leading edge. This is called a winter check mark. And so from 1 minute winter check mark to the next winter check mark is the coldest time of the year to the next coldest time of the year. And effectively for us, it's like sometime in January to sometime in January. So this is a full year. This is a full year. You can see that there's sometimes little lines in them here that are, and these lines can be from bad storms. If you have a really bad stormy period for a week, they'll shut down a bit and you'll begin to get one of these things. But these much more solid lines, winter check lines, are pretty clear to see. And they vary by species. Some species are better to work with them than others. And there's both high-tech and low-tech ways of doing this and counting these rings. But basically what you want to do is you want to look out at the leading edge, the growing edge of the shell to where the clam is growing, and express the interval from the last full winter check mark as a percentage of the full year. And that's basically the underlying concept for doing this. The Veneride clams are better to work with than mussels. Mussels have an irregular shape to them. And I would tell you that working with mussels is a lot harder. These are the steamer clams, and if you look here, the winter checks form these more developed rings. So here's one here, here's one here, there's another one there. And what you'll see in both of these, and here's a butter clam, there's a winter check ring, here's a winter check ring, here's a winter check ring. As the animals get older, the rate of growth slows because they're putting energy into reproduction and sexual activity. And so the distance between the annual rings gets smaller and smaller, harder to read. The younger ones, the gaps are bigger, it's easier to tell what's going on. And for these two, both of which very common in Western Washington, a steamer clam will live 10 or 15 years. A butter clam can live 60 years or more. So a big butter clam is going to have really complicated check rings, winter check rings, and it'll be hard to sort out. Steamers are better to work with. And for Ozette, what I did was, because I had thousands of steamer clams in the collection, the archaeological collection, I went through and I pulled 120 full complete valves where I was pretty confident I could see the last 3 complete years. And then I took the average width of the last 3 complete years, and then I expressed the growth since the last winter check ring as a percent of that average growth over the 3 years prior to it, just to scale it out. And for a lot of this stuff, if you're really going to do these kinds of studies, collect samples off the beach where you're working. And so what we did for the steamer clams is for a 12-month period, mostly in 1979, started in December 27th of 78, went around to December 3rd of 79. I collected steamer clams and took at least 5 individuals at each time, more because we had a nice meal, measured the rings growth at that point in time, and then calculated an average for the 5 and plotted it year 1. And so this is the graph that I actually got. 0 and 100%, because it's a full year of the same thing. That's that midwinter cold period. And these are the dates I got. And so I got 30%. On March 18th, I was just over 30%. April 21st, I'm just over 40. June 1st, a little over 50, all the way up to December. And I had to tell you, I was a little disappointed with this range of numbers, that they were so compacted. I was hoping for something that had a little bit broader separation across the year. And of course, I asked Art Farrow at Peninsula College again. I said, well, doesn't that look kind of compressed? And that's not really the distribution I was hoping to see over the course of the year. And he said, well, yeah, but you had a long winter and spring was late. And then he told me that, if I did this for 5 years rather than 1 year, I'd probably have a better distribution, a more even distribution. But anyway, this is the distribution we had. And basically, it's not super high resolution, but I took the position that looking at this range for my modern sample, I decided that I'm going to say that 0 through 40% represents late winter and early spring. I'm going to say that from 40% to 70% represents late spring and summer. 70 to about 85% is fall. And then over 85% is early winter. Not high precision seasonality, but enough to kind of break up the year. When I do that for my 120 specimens, that's what the distribution looks like. And we can see that the highest amount of activity is late winter and early spring, when people who think of shellfish as a starvation resource would say, well, yeah, that's when we'd expect to see people using it. Late winter and early spring, spring is late, the stored food is run out, you go eat clams. But what the ring growth tells us is collecting continued through the summer months at a level that's almost as high as late winter and early spring, declines in the fall, and early winter, there's not much collecting going on, is what this pattern looks like. And this is consistent with what ethnographies tell us about Northwest Coast people. So there's some basis looking here for uh, considering that we have what do you call it, starvation harvesting, but harvesting continues through the summer when people are not starving with this animal. Okay, now let's look at size class selection for a little bit. Well, size class selection, I'm going to give you a little bit of background on the basis for looking at size class selection. Ecologists like to talk about animals that are R strategy or K strategy, reproductive strategies. I don't know if people are familiar with any of this discussion, but an R strategy animal is an animal that produces young in vast numbers, but has almost no parental involvement with them at all. And large numbers of them die off when they're young, and only a small percentage of them really go on to be adults. And that's in contrast with case strategy animals, of which humans are a really good example, because case strategy animals don't reproduce in large numbers, and they put a lot of parental involvement into the animals, into their young, and the adults stay with the young and raise them for a long period of time. Okay, our strategy animals, and shellfish are our strategy animals, produce in really large, giant numbers. And the parents have no involvement with them at all. They don't raise them, they're on their own. And so a typical R strategy population curve, if we looked at a sample of bivalves in terms of size, and I've already told you, size is related to age. Small ones are young, really big ones are old. We should see a population curve with large numbers of small ones, a moderate number of medium-sized ones, and only a small number of really large ones that are really old. And that's what the population curve should look like in a natural population. Okay, and so now let's look at some population size class for the primary prey bivalves at OZ. And first off, I have to tell you, when we look at this graph, this is kind of, it's not really log paper, but we try to come up with some variation on log paper to show different scales. And on the horizontal scale, you notice these are 1 centimeter increments to 8, and then they go to 2 centimeter increments. And on the vertical scale, these are single percents between 1 and 20. Then we jump to 10 centimeter scales, and then we drop back to single ones on the top. And basically, this was done because I really wanted to exaggerate the tails on the distributions. I was really interested in here and down here. And then also for the 5 major bivalves, the 2 with the blue lines are the epifaunal ones, the mussels that are outside on the rocks. Protothecus, Dominia, this is the steamer clam, butter clam, horse clam. Those are things you got to dig for. Okay, looking at the bottom of the curve first, we see that the very small ones for mussels are pretty high percentage. 1 centimeter California mussels are almost 20% of the curve. Blue mussels are more than 30%, the tiny ones. In contrast, the butters, the steamers, and horse clams, the small ones are much, much lower percentages. And I think that what we're seeing here too is the mussels I told you are aggregated in these large piles that are all aggregated together. And people are mass harvesting those piles. They're not just picking the big ones. They're getting the whole batch of them together. And we see that described ethnographically. And we can see that here. For the butter clams, the steamer clams, people are more hand picking them, and they're looking for bigger things. They're not taking the smallest ones. And if we look at the horse clam, this last one here, Specimens smaller than 6 centimeters are less than 5% of the assemblage. And if you go out with macaw shellfish collectors now, they'll tell you that the horse clams are much more deeply buried than the steamers and the butters. And they locate the clam by the blowhole, the siphon hole on the surface. And the clam hunter is literally making a judgment about how big the clam is by the size of the hole. And this distribution here makes it very clear that these clam diggers are not bothering to dig deeper for horse clams unless they're at least 6 or 7 centimeters in size. They're selecting for bigger ones. There's simply not much interest in these small ones. Similarly, at the top of the distribution, most of these distributions top out pretty quickly, but you can see that California mussels and horse clams have a big tail at the top end of the distribution. And this is about artifact selection. The mussel shell blades, the harpoons that people are making out of California mussel shell, you need big valves to do that. You can't do it with a small valve. So they are deliberately selecting for the really big ones for tool stock. And in fact, we know people tell you, well, the really big old ones are tough. They're not all that tasty. So this is about harvesting tool stock. And the same thing with the horse clams, and it's about using shells for vessels. So we could see a fair amount of different selective action here going on with the shellfish. Okay, now here I've taken the same 120 samples that I have seasons on, and the bottom here is the ring growth. So here's our percent of ring growth. And here I've now taken the size classes for the steamers, and I've cross-cut the steamer size with the ring growth. And here is the distribution that results. Now, if I add the seasonal breaks for my seasonal scale to the distributions, we can see that the bulk of the collecting is going on late winter through early spring and late spring through summer. And there are two very distinctly different size class distributions going on here. In late winter and early spring, we have a distribution that has large numbers of small individuals, moderate numbers of medium-sized individuals, and a few big ones. This is very much what a non-selective sampling of the shellfish would look like. If somebody just went out there and took every one, didn't really care much about size, we would have this kind of distribution. Excuse me. We would have this kind of distribution. This is consistent with the starvation model, that people are hungry and they're not worried about just big ones or just small ones. This distribution, which is statistically different from this one, and I don't have the indices offhand, but we've run some tests on them, and I think it's obvious if you just look at them. In the summertime, they're selecting for big individuals. They're not really interested in small ones. They want mostly big ones. So this is high degree of size class selection. This is almost no size class selection. And the traditional elders in Neah Bay, when they saw this, they kind of laughed and they said, well, yeah, that's easy to understand. In the summertime, you're mass harvesting clams and smoking them to dry them so that you can trade with them or you can consume them at some other time. And you smoke them in the smokehouse the same way you smoke fish. And the fact of the matter is the shellfish meat shrinks when you dry it. And so if you start with a small clam and you put it on a stick and you hang it in the smokehouse, it shrinks so much that it really gets tiny or it breaks off the stick and falls on the ground. If you start with big clams, then that's not really a problem for you because you can deal with the shrinkage and it stays on the stick. So when we look at seasonal growth and we compare it to size classes, we can see that they're doing different things in different seasons. And it's sometimes of the year when they want immediate consumption, they're not worried about size, they're going to take anything. Other times of the year, when they're more looking at deferred processing for deferred consumption. Size class is more of an issue, and people are actually exercising selection in the summertime that they're not exercising in the late winter. Okay, a few other things here. I just want to go through here a little bit about looking at social space. Okay, in this graphic here, I've have my functional categories that I told you about, and the vertical axis is the percentage of M&I occurrence in exterior midden deposits outside of houses. And we further arbitrarily said that if the percentage of M&I occurrence in exterior deposits is less than 30%, we're going to say that's a strong interior bias. And if it's more than 70%, it's a strong exterior bias. This corrected and uncorrected thing we don't need to worry about now. But basically, incidental stuff, primary foods, inadvertent secondary prey things, these are mostly food or oddball stuff. Mostly more than half of that stuff you find outside houses, not inside houses. Alternatively, Olivella shell bees, ground shell tools, all decorative, symbolic and ceremonials, and exotic decorative. These are trade items like the dentalium. These things are curated. People are not discarding them like they discard food residues. These things have strong interior biases. In fact, the things like dentalium are almost never found outside the houses. The people hang on to them, they're exotic, they're valuable. And so the distribution between interior and exterior surfaces really varies depending upon why the shell is there in the first place and what its function is within that context. Okay, another way we can look at this is we got 4 houses at OZ. And here I've just summarized 7 taxa and their proportion, and I've totaled these 7 to 100%. And here we have the contents of 4 houses. 3 is not a complete house, but we have probably 30% of it. The rest are all complete houses. And when we look at them side by side, we can notice some similarities and some differences. And first off, house 1, and that's the lower house on the beach, on the bank where the house fell off first. Almost 8% of these materials of the shell of that house within this group is dentalium, a highly valuable trade material from Vancouver Island, extremely high valuable wealth object. No other house has any. This is a high status house because there's a couple of hundred of them here. Okay, beyond that, house 1 has dentalium and none of the others do. If we look at the ratio of steamer clam, well, actually, first off, before we do that, look at blue mussel. California mussel is the dominant in all houses. Blue mussel. And you remember earlier when I showed you that map of different habitats at Cape Alava, I told you that blue mussel is only available at the mouth of the Ozette River. It comes from a very single localized spot, and it's the only place in the area you can get it. People in house 1, house 2, and house 3 are collecting at the river. People in house 5 are not collecting at the river. Further, if we look at the ratio of steamer clams to butter clams, the ratio of steamers to butters in house 1, house 2, house 3 is similar. It's different in house 4. Now, we know from oral history and ethnographic accounts that the right to take shellfish was controlled by lineal groups. Not anybody in town could go dig shellfish anywhere they wanted. Different portions of the beach were controlled by different families. And this is a resource regulation mechanism, because if everybody collected on the beach in front of the site, they'd wipe it out quickly. And I think from this distribution here, that we have good grounds to suggest that the residents in house 1, house 2, and house 3 are members of the same lineal group. And we're collecting off the same suite of beaches. House 5 represents a different lineal group, and they are collecting off a different combination of beaches in the area, but it's clearly distinct from these. So among the four houses, we can argue that three of them are lineal related, and house one is the high status household. And house five represents a different group of people. In fact, we could use this to argue, unlike what I said earlier, that the people who built house two are not the same people who built house five, because the house two people are clearly part of this group, and the house five people are not. They are collecting a different combination of beaches in the area. House floor patterns. And we'll just wrap this up. I'm running a little longer than I thought I would, but we'll still finish this in time. Remember I told you about how we use house floor patterns, both the nuclear family areas around the hearth. Each nuclear family area had its own hearth, and then this bench zone and central zones on the house floor. And if we look at the distribution of things on the house floor, looking at house one, this is a point plot of all the artifacts on the house one floor. 4,470 of them. And one of the things that I think you can see real clearly here is the highest densities of artifacts are in the bench zone. They're under the benches where nobody is walking. People are sweeping stuff. And in fact, we know that they were sweeping on the floor. And so there are other stuff, other traffic zones on there, but most of the bulk is up against the walls, underneath floors, places where nobody's walking. Okay, this is a SimMap. And I know this is older software, but basically this is to take all the shell densities and look at density patterns on the house one floor. And here, this is all shell, not separated by taxa. This is the total amount of taxa. And we can see that the highest density of shells is over here toward the northeast corner. And the second high density is in the southeast corner. And while we don't have the west wall of the house, this is the beach side, we can see, we know this floor was swept and regularly, and there's other, not through the shell materials, but for other things that have been looked at in the house floor, there's good evidence that this floor was swept regularly. And the door was right here. You can see where stuff is being pushed out of the door. We know from ethnographic studies that the people who lived in the back corners of the house were the high status people. Higher status people live further away from the door, so that in sudden attacks, they're not surprised as easily. And in fact, oral history tells us that the guy in the back on the left, this nuclear family area here, is the house owner. And a lot of the internal feasting probably went on near his area, which is why we have these higher densities. And in fact, right here in that back corner is almost all the dentalium in house one. There was obviously a giant string of dentalium. Hundreds of pieces were hanging on the wall right back in there, and it collapsed. So this is a really high status situation here. And here's all of the California mussel, the single most abundant bivalve. And again, we see nodes back in here where a lot of food is being consumed, more in there, some places on the house floor. And I've already told you, and I'm just about done here now, that California mussels were mass harvested. We have ethnographic information that they're not picking them by hand, they're all aggregated together. They're taking a wood or a whalebone scoop and they're prying up big mats of mussel shell material, throwing them in the canoe, and they're bringing them back to the village. And these mats have mussels of all sizes. And these mats have things like Thias lamellosa, these little predatory gastropods in there. And the ethnographies tell us that this collection is done mostly by groups of women, sometimes women and children, who collectively collect this stuff and they bring it back to the house and then they divvy it up on the house floor, and individuals take their individual piles back to their nuclear family areas. And so one of the things that we did to look at that is to say, well, if that's what they're doing, then we would expect to see the discards from those unpacking of the piles on the house floor, out in the middle of the floor. And so here's a map of just the 1 centimeter California mussels. And you remember when I showed you all of them, we had high densities back in this corner and in this corner. But what we're seeing now are more piles on the floor out in the middle of the floor for the tiny ones. And here's the dog winkles. Here's Thias lamellosa. Same kind of pattern. These things are not really going back to the high density food areas. They're being separated out and discarded on the house floors. Okay, because I don't want to completely run out of time without taking questions, just some summary comments. Okay, first off, I think you can see that at Ozette, there's a lot of things we can do, but honestly, we looked at 300,000 pieces of shell. I personally didn't identify more than about 25 or 30,000 of them. Almost 10 people worked on that. It's not a lot of situations where we could do that. But I think even if you don't have giant sample sizes, as I describe here, it's probably a lot we can learn from shellfish at most of the shell midden sites in Western Washington. And I could see people going like, well, gee, okay, well, that's really cool, but you had a small army of people to do it, and this was really labor intensive. I mean, this was worked on for several years to do. And it is really labor intensive. There's no question about that. And I talk to people who go, well, Jesus, look at the amount of energy you put into all these shells to do that. On the other hand, I can tell you in the early 1970s, in my own personal pre-classic period as an archaeologist, I worked for ceramic archaeologists in Mexico. And they didn't think of any problem at all at looking at 30,000 pieces of broken pottery. And frankly, I know lithic analysts who don't have any problem with looking at 10,000 pieces of debitage to measure platform angles. So to me, the fact that this is labor intensive, this kind of goes with the territory. Archaeologists do lots of things that are labor intensive, and I don't think this should be segregated just because it's about shells. And I've been kind of talking a bit in recent years about getting more from less, because I think as we look at what archaeology is doing in this country now and in the near future, the large scale excavations like Ozette and Hoko and these large mega projects are going to become less common. CRM testing will become much more common, and we need to find ways to get more information out of smaller samples. And to me, describing the sample material better so that there's more analysis you could do with them is a key way of getting more for less. And additionally, I would say in the CRM world, shell midden deposits are quite common in Western Washington. There's at least 1,400 of them recorded. There's probably a lot more that haven't been recorded. And CRM and shell middens are often subjects of CRM review, and they typically don't contain a lot of artifacts. And so CRM analyses focus on whether the deposit is intact or not, because that's the key eligibility issue. But we don't get a lot of behavioral information out of most small volume CRM tests of shell midden deposits. And I submit that there's a lot of cultural information that can be obtained from faunal remains, not just shells, the vertebrate remains as well. And that's what we need to be doing as we're going to continue to generate more small volume samples and limit ourselves to just wanting to talk about artifacts. The faunal samples, the shellfish and the vertebrate remains can be rich sources of cultural information if we're prepared to invest in the samples to have highly detailed descriptive information and detailed models of behavior to test them with. And I guess that's really my major point here. And I would say as the last thing here, and just a thought here, I gave this talk or talk similar to this actually for the AWA about 20 years ago. And when I summarized at the end, I offered a quote from Bill Graham. And maybe that's just my age showing, because most of the people in the room had no idea who Bill Graham was. And just for those of you who might know or recall if I mention him, Bill Graham was a concert promoter in San Francisco. He had a place called the Fillmore in the 1960s and 70s. that was a central place for a lot of the rock music that came at that time. And Bill Graham used to like to say that if you want to dance, you got to pay the band. Uh, and if you want to learn things about shell deposits and these complicated deposits, well, you gotta make the investment in the front end. But there's lots of things that can be learned. He's really okay at the end. Then telling me all about shell beads or in my site, the Kittitas Valley. Yeah, no, these things are traded across. Absolutely. Sometime, in fact, there's all the Vela seeds, the shell beads is into Western Montana, actually. Um, I'm not aware of them, although they certainly could be in decorative things. I'm just thinking when you say that about masks and other ceremonial art, uh, but I really can't think of an example offhand where the spines themselves would have been used. You know, most dry shell middens have most of the artifacts in Western Washington are bone objects. Some parts of Western Washington have a fair amount of chipstone in the middens. Other parts don't. On a lot of the Olympic Peninsula, particularly the Western Olympic Peninsula, we don't see very much chipstone. And frankly, the most common types of bone artifacts in these middens are bone points, which are the bone element and composite tools, fish hooks, harpoon barbs, herring rakes, and and if you look at the OZ collection, I mean, if people are interested in the bone points, go out to the museum in the Bay sometime. We have all the bone points in situ in different types of fish hooks and herring rakes and other types of things, where we can see the complete composite artifact, where we have the bone point, the wood haft, the cherry bark wrapping. But in dry shell middens, all you really are going to get are the bone. And so large numbers of bone points not associated with the composite tools they represent are extremely common in these deposits. Acorn barnacle remains are commonly mistaken for fish scales, and sometimes, yeah, a lot of things can be mistaken. I showed the octopus beaks. The guy who was doing faunal analysis in the early days of the OZEP project uh, thought that they were parrot bills and might have represented some kind of long distance trade from Mexico. They're not, they're octopus beaks. but yeah, there is confusion here. Sand dollars occasionally show up in middens, but you don't usually find very many, and there's not much in a sand dollar that's really edible. Uh, but people pick up stuff. As a matter of fact, I can tell you that there are two shell middens in Western Washington that when they were excavated, they recovered a fossil shell. The Menard site down there at Grays Harbor has a fossil cockle, a fossil clinicardium. Looks just like a cockle, but it's a fossil. And I personally, some people have said, "Oh, is that some kind of sacred object?" I don't know. I think it could be a paleo practical joke. I could imagine that it was served to people many, many times over the years. And actually, there's another midden on the Macaw Reservation, a 3,000-year-old midden, CA 400, that has part of a fossil moon snail in it. And I think these are things that just people notice, walking around, and they saw it was possible, but they recognized that it was a shellfish. It was the shape and the form they recognized, and somebody picked it up and brought it back. And those can be used to count. I mean, that's one of these other internal structures that can be used to count MNIs if you have them intact in your deposit. You're really going to have to go through a lot of sea urchin tests to do that. And I would argue that you're still not going to get a really complete number, but yeah, that can be done. I tend to think of it that the collecting rights are kind of a complete package. I think to a certain extent, individual preference plays into this a little bit, but some people just like certain types of shellfish more than others, so there's some variation. But the fact that houses one, two, and three are all collecting up at the river mouth for blue mussel, and house five is not, and that the butter steamer ratios are similar too, I think is a pretty strong argument. And those are more important resources than the chitons are, probably. Hard to say, but I think that the house one, two, and three are probably related, and house five is not. This is kind of the way I do the math on that. Cool fossils confirm that the timeless tradition. Yeah, people do that. Um, yeah, okay. I would tell you further because I would really like to see more people doing this kind of work, even though it is kind of daunting. But it's, MA theses, PhD, stuff like that. If anybody is interested in getting copies of the templates that I have, contact me, and I'd be happy to make you a set of them. And really, for a lot of these things, I mean, anybody who's interested in doing this needs to learn the shellfish. You need to have a good comparative collection, and you get that by just walking beaches, and picking up stuff and learning the shellfish. And I don't have templates for all the bivalves, but if you have a site with lots of cockles, for example, pick up shells off the beaches and make your own templates. It's a little bit of time consuming to do, but it's not going to add that much more time to the actual coding of the shells. And having that size information to cross-cut with other characteristics, like for looking at size class selection, it really opens up new opportunities to look at things in terms of what collectors are doing that really not accessible to us otherwise. Okay, go out there and do cool things.